School of Management Studies IGNOU presents an audiobook on the course MMPC 008 Information Systems for Managers for MBA program. Block 4 Support Systems for Management Decisions. Unit 13 Data Warehousing and Data Mining. Part 1.
Introduction. Use of IT in all the fields and business sectors is well known today. Developments taking place have made information communication very easy. A smartphone is sufficient today to generate and disseminate information across without barriers. Same information is possible today to make available over many channels through emails, social media, messaging system, and so on in unified way. Automation of day-to-day activities, availability of internet in every nook and corner, ease of governmental policies in starting businesses, use of IT by one and all in business are producing more and more volume of data which are used today for various analytical purposes. Such analyses are also used for proactive strategic decisions. Availability of resources like cloud computing, SaaS, software as a service, PaaS, platform as a service, etc. have made it possible to dig out data from around the globe. In this unit, we will discuss the concept and use of data warehouses in terms of how they have evolved, matured, and taken the world of business by storm. Objectives. After reading this unit, you should be able to identify the types of data in data warehouse, describe the design decisions involved in data warehouse design, explain the importance of building an enterprise data warehouse, depict the architecture of a data warehouse and its various components, describe various aspects of star and snowflake schemas, define and explain the concept of metadata in the data warehouse, enumerate the importance of external data feed from the World Wide Web to the data warehouse, describe the process of data analysis and online analytical processing, develop a case for the business value of visualization of data, and apply data mining tools for discovery of hidden relationships and patterns in business data. Operational and informational databases. There are several reasons that have compelled information system designers to accept that even the latest technology cannot be optimized to support both operational and informational processing in a cost-effective manner. The reasons may be like following. The data required is different. The information required is different. The technology required is different. The user community is different. The access pattern is different. The processing characteristics are different. The system loading pattern is different, and furthermore, high-level business objectives provide the framework for competitiveness and growth to an enterprise in the long run. To set realistically achievable objectives and monitor the company's performance against them, managers need information on subjects like customers, products, and distributors. It is also beneficial to aggregate measures like quantities of products and sales value across various dimensions like geographical regions and time, and compare them with yardsticks like budgets, forecasts, previous year's actuals, and industry average. In today's world, surrounded by IT and its application, it is more imperative as they may be considered as the basic requirements for online businesses. Information systems have evolved from the master file or transaction file and sequential processing of the 1960s to DBMS-based random access processing of the 1970s to high-performance transaction processing during the 80s to decision support system built around the existing operational, informational, and virtual databases. The traditional IT departments with limited resources, when faced with the need to provide strategic information using data in operational databases, find themselves inadequately equipped to respond. Some of the difficulties faced are IT receives too many ad hoc requests, resulting in a large overload. With limited resources, IT is unable to respond to the numerous requests in a timely fashion. Requests are not only too numerous, they also keep changing all the time. The users need more reports to expand and understand the earlier reports. The users find that they get into the spiral of asking for more and more supplementary reports, so they sometimes adapt by asking for every possible combination, which only increases the IT load even further. The users have to depend on IT to provide the information. They are not able to access the information themselves interactively most of the time. The information environment, ideally suited for strategic decision making, has to be very flexible and conducive for analysis. IT has been able to provide such an environment. The solution to the problems lies in the paradigm, the data warehouse. It is an environment that is specifically designed to hold data required to support complex analysis and detection of patterns, trends, and deviations. The characteristics of such an environment can be summarized as follows. Provides an integrated and total view of the enterprise. Make the enterprise's current and historical information easily available for decision making. Makes decision support transactions possible without hindering operational systems. Renders the organization's information consistent. Presents a flexible and interactive source of strategic information. The data warehouse. We have understood the need and importance of data warehouse to facilitate strategic decision making. The defining characteristics of a data warehouse are subject orientation. Data warehouse data of an organization are arranged and optimized to provide answers to questions coming from diverse functional area within a company. Therefore, the data warehouse contains data organized and summarized by metadata and keywords, that is, by topic such as sales, marketing, finance, distribution, transportation, etc. For each one of these topics, the data warehouse contains specific subject of interest, products, customers, departments, regions, promotions, and so on. Note that this form of data organization is quite different from the more functional or process-oriented organization of typical transaction systems. Time variancy. We have already noted that the DSS data include a time element. In contrast to the operational data, which focus on current transaction, the warehouse data represent the flow of data through time. The data warehouse can even contain projected data generated through statistical and other models. Non-volatility. Once data enter the data warehouse, they are never removed. Because the data in the data warehouse represent the company's entire history, the operational data representing the near-time history are always added to it. The near-time history information is gathered and stored by data collecting IT tools. One such example by IBM is Omegamon XE for their DB2 RDBMS. Because data are never deleted and new data are always added, the data warehouse is always growing. That is why the DSS DBMS must be able to support storage in terms of multi-gigabyte and even multi-terabyte database and multi-processor hardware. However, based on the organizational policy, an organization may take decision to remove old data from the warehouse after a period of, say, 10 years. It may also be possible to offload such data to another secondary storage for references in future. Integration. The data warehouse is centralized, consolidated database that integrates data derived from the entire organization. Thus, the data warehouse consolidates data from multiple and diverse sources with diverse formats. Data integration implies a well-organized effort to define and standardize all data elements. This integration effort can be time-consuming, but once accomplished, it provides a unified view of the overall organizational situation. Data integration enhances decision-making and helps manager to better understand the company's operation. This understanding can be translated into recognition of strategic business opportunities. The load manager. Data flows into the data warehouse through the load manager. The data is mostly extracted from the operational databases and other internal sources like archived historical data and supplemented by data imported from external sources. Externally sourced data can greatly enhance the value of information generated from a data warehouse. For example, a gas pipeline operator in Western countries like UK, USA, Canada, etc. may use weather forecast data from the country's meteorological office on a regular basis to determine demand for gas in various areas of the country. The weather data may be fed into a model incorporating several other factors. Example, day of the week internal data about customers' usage patterns, demographic and economic profile data, alternate sources of energy, types of building in the area, to arrive at a demand forecast. Types of data from external sources that may be included in data warehouse are financial indicators and statistics of the industry, market share data of competitors, demographic data, weather data, credit worthiness data, readership viewer survey data for advertising media, specially commissioned surveys, and so on. External data is usually obtained from the commercial database services or government agencies. The data from such diverse sources will obviously be in different incompatible formats and will be distributed through various media. Some of them may be available on a downloadable format from virtual databases on the internet. Others may be distributed on secondary storages, while some may only be available on printed media. Some data may be available for free, but most data, particularly when used for commercial purposes, have to be purchased. The load manager primarily performs what is termed as an extract transform load (ETL) operation. Data extraction, data transformation, data loading, data extraction. This function has to deal with numerous data sources. Appropriate techniques have to be employed for each data source. Source data may be from different source machines in diverse data formats. Part of the source data may be in relational database systems. Some data may be on other legacy network and hierarchical data models. Many data sources may still be in flat files. There may also be the need to include data from spreadsheets and local departmental data sets. Data extraction can become quite a complex operation at times. Various tools are available on the market for data extraction. Use of outside tools may be considered suitable for certain data sources. For the other data sources, in-house programs may be also needed to be developed to do the data extraction. Purchasing outside tools may entail high initial costs. In-house programs, on the other hand, may mean ongoing costs for development and maintenance. After extraction, the data needs to be kept somewhere for further preparation. Sometimes the extraction function is performed in the legacy platform itself if that approach suits the designed framework. More frequently, data warehouse implementation teams extract the source data into a separate physical environment from which moving the data into the data warehouse would be easier. In the separate environment, the source data may be extracted into a group of flat files or an intermediate relational database or a combination of both. This physical environment is called the data staging area. Data transformation. In every system implementation, data conversion is an important function. For example, when implementing an operational system such as a magazine subscription application, the database has to be initially populated with data from the existing system records. The conversion may either be from a manual system or from a file-oriented system to a modern system supported with relational database or object-oriented tables. In either case, the data will need to be converted from the existing systems. So, what is so different for a data warehouse? Why is data transformation for a data warehouse more involved than that for an operational system? As already discussed, data for a data warehouse comes from many disparate sources. If data extraction for a data warehouse poses great challenges, data transformation presents even greater challenges. Another factor in the data warehouse is that the data feed is not just an initial one-time load. The ongoing changes will have to continue to be picked up from the source systems. Any transformation tasks are set up for the initial load will have to be adapted for the ongoing revisions as well. A number of individual tasks are performed as part of data transformation. First, the data extracted from each source is cleaned. Cleaning may be correction of misspellings or may include resolutions of conflicts between SAT codes and PIN codes in the source data, or may deal with providing default values for missing data elements or elimination of duplicates when the same data is brought in from multiple source systems. Standardization of data elements forms a large part of data transformation. The data types and field lengths for same data elements retrieved from the various sources need to be standardized. Semantic standardization is another major task. Synonyms and homonyms have to be resolved. Resolution of synonyms is required when two or more terms from different source systems mean the same thing. On the other hand, when a single term means many different things in different source systems, resolution of homonyms have to be performed. Data transformation involves many forms of combining pieces of data from the different sources. In some cases, data from a single source record or related data element from many source records are combined. In other situations, data transformation may also involve purging source data that is not useful or separating out source records into new combinations. During data transformation, sorting and merging of data takes place on a large scale in the data staging area. In many cases, the keys chosen for the operational system are field values with built-in meanings. For example, the product key value may be a combination of characters indicating the product category, the code of the warehouse where the product is stored, and some code to show the production batch. Primary keys in the data warehouse cannot have built-in meanings. Therefore, data transformation also includes the assignment of surrogate keys derived from the source system primary keys. A grocery chain point of sale operational system keeps the unit sales and revenue amounts by individual transactions at the checkout counter at each store. But in the data warehouse, it may not be necessary to keep the data at this detailed level. It may be more appropriate to summarize the totals by product at each store for a given day and keep the summary totals of the sale units and revenue in the data warehouse's storage. In such cases, the data transformation function would include such summarization processing. The end result of the data transformation function is a collection of integrated data that is cleaned, standardized, and summarized. Now, the data is ready to be loaded for populating the data warehouse. Data loading. Two distinct groups of tasks form the data loading function. After completion of the design and construction of the data warehouse, when it goes live for the first time, the initial loading of data is done. The initial load moves large volumes of data, which may take substantial amount of time, but it is one-time effort. As the data warehouse starts functioning, extraction of additions and changes to the source data continues on an ongoing basis together with the transformation and loading operations. The Query Manager. The Query Manager provides an interface between the data warehouse and its users. It performs tasks like directing the queries to the appropriate tables, generating views on an ad hoc basis if required, monitoring the effectiveness of indexes and summary data, and query scheduling. Data warehouse design considerations. The key considerations involved in the design of data warehouse are time span. Operational data represent current atomic transactions. Such transactions might define a purchase order, a sales invoice, an inventory movement, and so on. In short, operational data cover a short time frame. In contrast, data warehouse data tend to cover a longer time frame. Managers are seldom interested in a specific sales invoice to customer X. Rather, they tend to focus on sales generated during the last month, the last year, or the last 5 years. Rather than concern themselves with a single customer purchase, they might be interested in the buying pattern of such a customer or groups of customers. In short, data warehouse data tend to be historic in nature. That is, the data warehouse data represent company transactions up to a given point in time, yesterday, last week, last month, and the like. The time period for which data is held in the data warehouse is determined by the data analysis requirements of the users of the data warehouse. These needs, in turn, arise from the changes in the business environment that a particular organization needs to monitor in its effort to stay ahead of its competitors. Since a data warehouse's size depends on the span of time for which data is stored, the time span covered by the data warehouse is an important design consideration. If, for example, the environment changes rapidly, the data required for analysis would relate more often to the recent past rather than that over several years or decades. In that case, the designers of the data warehouse need to consider whether or not the cost incurred in holding data for indefinitely long time spans would be worthwhile. Granularity. According to Inmon, the single most important design aspect of a data warehouse is the decision or granularity. It refers to the level of detail or summarization available in units of data in the data warehouse. The more detail there is, the lower the level of granularity. The less detail there is, the higher the level of granularity. Operational data represents specific transactions that occur at a given time, such as customer purchase of product X in store A. Thus, granularity is taken for granted to be the lowest level. In operational systems, data warehouse data must be presented at different levels of aggregation, from highly summarized to near atomic. This requirement is based on the fact that managers at different levels in the organization require data with different levels of aggregation. It is also possible that a single problem requires data with different summarization levels. For example, if a manager must analyze sales by region, he or she must be able to access data showing the sales by region, by city within the region, by store within the city within the region, and so on. In this case, the manager requires summarized data to compare the region, but he or she also needs data in a structure that enables him or her to decompose the data into more atomic components. For example, it is necessary to be able to drill down to the stores within the region in order to compare store performance by region. Granularity level in a data warehouse cannot therefore be assumed. The decision on granularity level profoundly affects both the volume of data that resides in the data warehouse and the type of query that can be answered. A trade-off exists between the volume of data in the data warehouse and the level of detail of queries. Some data warehouses are designed to support dual granularity. In such environments, some data is held at a relatively low level of granularity, while the rest is held in more summarized form. This enables detailed analysis at the same time, allows reduction of data volume. Dimensionality. This is probably the most distinguishing characteristic of a data warehouse. From the data analyst's point of view, the data is always related in many different ways. For example, when we analyze product sales by a customer during a given time span, we are likely to ask how many widgets of type X were sold to customer Y during the last 6 months. In fact, the question tends to expand quickly to include many different data dimensions. For instance, we might want to know how the product X fared relative to product Z during the past 6 months by region, state, city, store, and customer. In this case, both place and time are part of the picture. In general, Data analysis tends to include many data dimensions, producing a multidimensional view of the data. The data model used for modeling data warehouses is known as the dimensional model. The numerical measurements related to the business are stored in fact tables. The descriptions of the dimensions are stored in dimension tables. We will discuss this in more detail in later sections. The number and types of dimensions and facts that are to be stored in a data warehouse is a very important design decision and affects both the data volume and the types of analysis that can be supported. Aggregations. We have seen how data analysis queries directed at data warehouses involve dimensions. Another very common type of query directed at data warehouses involves sums of values along the different dimensions. For example, what is the total sales volume of VCR during the past 4 quarters? Answering this query using the fact and dimension tables would involve summing up the individual sales volume figures over the 4 quarters and the 3 counties. In real situations, similar queries might involve retrieving and summing hundreds or thousands of individual values. To avoid excessive processing load on the data warehouse arising from frequently asked queries of this type, it is often decided at design time to store some pre-calculated aggregations along with the base facts in the data warehouse. This decision affects the data volume and performance of certain types of queries. Partitioning. One of the essences of the data warehouse is flexible data storage, management, and access. When data resides in large physical units, among other things, it cannot be indexed easily, sequentially scanned if needed, restructured easily, backed up conveniently, recovered easily, monitored easily, and so on. In short, having a big mass of data defeats much of the purpose of the data warehouse. The purpose of partitioning is to break the data into smaller physical units of storage. The criteria used for dividing the data can be date, line of business or product category, geography or location, organizational or administrative unit, or any combination of these. Data warehouse schema. One of the key questions to be answered by the database designer is, how can we design a database that allows unknown queries to be performant? This question encapsulates the differences between designing for a data warehouse and designing for an operational database and information system. In a data warehouse, one designs to support the business process rather than specific query requirements. In order to achieve this, the designer must understand the way in which the information within the data warehouse will be used. In general, the queries directed at a data warehouse tend to ask questions about some essential fact analyzed in different ways. For example, reporting on the average number of light bulbs sold per store over the past month, the top 10 most viewed TV programs from a TV channel or channels during the past week, top spending customers over the past quarter, customers with average credit card balances more than Rs 50,000 during the past year. Each of these queries has one thing in common. They are all based on factual data. The content and presentation of the results may differ between examples, but the factual and transactional nature of the underlying data is the same. Fact data possesses some characteristics that allow the underlying information in the database to be structured. Facts are transactions that have occurred at some point in the past and are unlikely to change in the future. Facts can be analyzed in different ways by cross-referencing the facts with different reference information. For example, we can look at sales by store, sales by region, or sales by product. In a data warehouse, facts also tend to have few attributes because there are no operational data overheads. One of the major technical challenges within the design of a data warehouse is to structure a solution that will be effective for a reasonable period of time. This implies that the data should not have to be restructured when the business changes or the query profiles change. This is an important point because in more traditional applications, It is not uncommon to restructure the underlying data in order to address query performance issue. The inherent advantage of factual transaction is that their content is unlikely to change, regardless of how it is analyzed. Also, the majority of the data volume of a data warehouse comes from the factual information. It is therefore possible to treat fact data as read-only data and the reference data as data that is liable to change over time. Thus, if reference data needs to change, the voluminous fact data would not have to be changed or restructured. Star schemas are physical database structures that store the factual data in the center, surrounded by the reference data. The dimension tables should be relatively small in comparison to the size of the data warehouse, so that restructuring costs are small as long as the keys to the fact tables are not changed. In star schema arrangements, the reference information is often denormalized to a single table to speed up query performance. The redundancy overheads are acceptable as the sizes involved are small and even the reference information changes infrequently. The dimensional information represented by the reference data is often organized in form of concept hierarchies that are used for analysis and designing data warehouse aggregation. The number of concept hierarchies that can be defined on any given dimension is by no means restricted to one. There may be several arbitrary concept hierarchies in use in any organization to enable data analysis from various angles. When the concept hierarchies and groupings are incorporated into a star schema diagram, hence, schemas of this type are called snowflake schemas.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 008, Information Systems for Managers. Course Coordinator, Professor Anurag Saxena, School of Management Studies IGNOU. Voiceover by Renuka. Edited by Uday Sharma. Program assisted by Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.